All right, we're gonna continue with the I2C discussion, and here we're gonna talk about the excuse me, the multi-master mode. So typically, I2C bus has only one master connected to the bus, along with multiple devices, and the master has the primary responsibility of initiating the communications. The master always initiate the communications, whether it is for write or reading purposes. The device themselves don't initiate the communications. So one of the issues occur is if there are multiple masters on the same I2C bus. We know that this is a feature. It is allowed to have multiple masters, but let's figure out how this is gonna work in a good way. So in the multi-master mode, the devices are aware there are multiple masters, and they're gonna activate these two schemes that we're gonna see here. The first scheme is called clock synchronizations. So multiple masters, they're gonna try to drive the clock signal, the clock line simultaneously. What's gonna happen when these two clocks signal clash? It turns out they're gonna clash into a usable signal. They're gonna collide constructively into a usable signal, and this gonna rely on the wired end property of the I2C lines. The wired end property means the low prevails. If multiple guys transmit a high on the wire and one guy transmit a low, the low will prevail because this is pull up to VCC. So anybody put a low, the state of the bus is gonna be a low. So these are the two masters. We have clock 1 and clock 2 belong to two masters. And if these clock clash, this is what's gonna occur on the bus. Let's see what happens here. At this point, all the masters are gonna synchronize and start counting their high duration. So let's see what happens. The master 1 is gonna put this high duration. The master 2 is gonna put this high duration. And they're both gonna do this, gonna be synchronized at this point. So what we're gonna observe on the bus is the shortest of all the high durations. Let's see why is that. The first master is gonna transmit this high duration and drop the line to low, but this guy is gonna transmit this high duration and drop the line to low. Knowing that low prevails, this is the first time a master will drive the clock line to low, and that's indeed what we will observe on the bus. Because the low prevails, so when multiple masters start counting their high at the same time, we're gonna observe the shortest of the high duration, just because the low prevails. So what happens next at this point is now all the masters start counting their low duration. They're gonna all synchronize up to this point, just like they all synchronize up to that point. So that's kind of like special feature. All the masters synchronize up to this point, and they start counting off their low duration. So what are we gonna observe? This master intends to put this low duration. This master intends to put this low duration. We know that the low prevails, so we're gonna end up seeing the longest low duration. So that's the resultant clock that we're gonna see on the line. So the resultant clock that we're gonna see on the line is gonna have the shortest high and the longest low. So it's kind of like a mix between these two signals. And this clock signal is actually usable. So when these two guys clash, the I2C communication is still gonna continue based on this clock signal. So that's the nice part, is they didn't collide into garbage, they collide into a signal that can be a usable signal. So one thing you can think about here, if there is another master, clock 3, or yet another master, clock 4, the same thing would happen. We would still get the shortest high of all the 4 of them and the longest low of all the 4 of them. So this procedure generalizes. Next, we're gonna look at the second scheme called arbitration. So if two masters collide, who's gonna continue and who's gonna back off? This is the purpose of arbitration, right? They cannot communicate simultaneously, so one of them has to continue, the other has to simply wait. So let's observe what happens here. The master one transmit this address, because we know that after the start signal, we're gonna transmit the address followed by the read or write bit. The master 2 plans to transmit this address, at least starting with these 4 bits. We're gonna see what happens here. So let's see what occurs on the data line. 1 and 1, the data bus will be 1. 0 and 0, the data bus will be 0. 1 and 1, data bus will be 1. This is the first bit where they differ. So this guy transmits a 0, this guy transmits 1. 0 prevails, the low prevails, so the status of the bus will be 0. So what's gonna happen here is this guy will know it has been preempted, because this guy basically transmitted a 1 and it observes the state of the bus and it sees a 0. So this guy knows that there are other masters who transmitted a 0, and simply means this guy will back off. It's not gonna transmit these 3 bits, and the first master will continue transmitting the 3 bits. As you can see, everything master 1 put on the line, they have gone through correctly. So this is the arbitration procedures. So summary of this is, if two masters collide the clock, they're gonna work out correctly. One of them will back off once they start differing by a bit. So couple of cases you can think about is, it seems that if you try to communicate to a lower address, then you have preference, because here you can see the lower address will prevail, right? So the master communicating with a lower address probably will have preference, will have higher priority. This considered just a randomized feature, so we're not giving too much attention to this. Another interesting case is, what if the two masters try to transmit to the same address, right? So that's they put the same address. They could clash on the read or write bit. What if the read bit is the same? They both trying to read. I think they will both read from it, not knowing that two masters are involved. So that could well happen. Next, we're gonna look at some of the reserved addresses in I2C. So we have this address, all zeros, followed by the W bit. This is referred to as general call. And that means the master is calling all the devices because we want them to do something. So we're trying to get the attention of all the devices. So it's a W, so the master can follow it with command bytes. And this particular byte, 06 hexadecimal, is a software reset. This means all the devices are gonna reset their configuration. One of the labs, which is lab number 9, we're supposed to configure a light sensor. So when the light sensor starts, it's in the default state, which is not really what we want. We're supposed to configure it. But if you want to send it back to the default state, we can do a general call. This followed by 06. The light sensor goes back to its default state that it usually starts at. Note that some I2C devices may not support the general call features. So this is kind of device specific thing. The next reserve address we have here is all zeros followed by R bit this time. So it turns out this is an alternative to the start signal. The start signal is kind of hard to detect because it is a falling edge on the data line. So basically, to detect the start signal, that's an instantaneous moment, and the other guy should be really listening to this. So if the start signal was not detected correctly because it's simply a falling edge on the data line, then we have this guy that lasts 8 bits, all zeros with the RW bit equal to R. Then when the other guy detects this, this will be interpreted as a start signal, which we call the start byte. So the place where this kind of make sense to utilize is if one of the receivers has a software implementation, which we call the bit banging implementation. And in software implementation, it's hard to detect the start signal because that's instantaneous. You would want your other guy running the software to keep listening all the time, which can be difficult to do. But detecting 8 bits, every bit lasts 1 bit duration. So every bit lasts a relatively long time compared to an instant drop of the line. So that's the purpose of the start byte. Next, we're gonna look at the 10-bit address. Typically, I2C devices have a 7-bit address, but we can also support 10-bit addresses. And it turns out these can coexist on the same bus. So you can have 7-bit address, 10-bit address devices all connected to the same I2C bus. I would say in the most popular case, we stick with 7-bit because this gives you 2 to the power 7 equal 128 devices. So very rarely you're gonna put more than that on the same bus. So let's figure out how the 10-bit address works. This is the I2C exchange. This is the start bit, follow address with R or W. And it turns out we're not gonna put a 10-bit address here because this will break the semantics. We want this chunk to be 8-bit, the byte to be 8-bit. So typically I2C device, every chunk of data is 8-bit, except the start and the ACK. These are 1-bit each. But every chunk of data is 8-bit, and we're gonna try to keep this semantics of 8-bit chunks of data. So when the master intends to communicate with a 10-bit address, it's always gonna start with a W. It's gonna transmit these 5 bits, 11110, follow by these 2 bits of the 10-bit address. So the first 2 bits of the 10-bit address will go here. Assuming the device will acknowledge, the next byte will contain the remaining 8-bit of the address. So if you take these 2 bits and these 8 bits, this will be the 10-bit address that the master is gonna communicate with. So the bottom line is gonna take 2 bytes transmitted in order for the master to convey the 10-bit address it wants to communicate with. Now, one interesting thing you see here is with 10-bit address, the master is always gonna start with a W because it's gonna follow up with this byte to specify the remaining address bit. It cannot start with R. So if it really wants to read from the 10-bit address device, it's gonna do a repeated start and change this to R. That's kind of the limitation of this setup. So now we're gonna look at the programming model of I2C. And basically we start with an initialization function. This gonna initialize the clock rate that we're gonna use. We're gonna specify that I2C module is actually working in I2C mode because that same module supports multiple protocols. And once we get, that's kind of like the similar to the initialization function of the UART. So once we configure it and it's running, then we can start doing communications. I2C is simple to set up the clock. We just do divide. We don't do modulate because the clock doesn't have to be extremely accurate since it is synchronized. So this initialization is a bit easier to write than the UART function, the UART initialization. So what we're gonna do in this code, we're gonna read register 70 on I2C device 33. And we're gonna pretend register 70 is a model number. So if you read the model number, we're gonna get this model number, hexadecimal 4742. That's the number of our class, just as an example. So this setup is the same setup that we did in class. So we go to I2C device 33, internal register 70, and when we read that, we get the 16-bit value that you see here, 4742. These are the 2 bytes we're gonna get. If you recap a little bit on this exchange, we're gonna start this exchange with write. So first we're gonna put the start signal. Then we're gonna address device 33 with the write bit, because first we're gonna write 70. So the device knows which one of the internal registers we wanna communicate with. Once we write 70, this goes into the pointer, the internal pointer register. Then we're gonna do a repeated start, address 33, and this time we're gonna do a read. And then we're gonna read 2 bytes. This is the first byte, that's the second byte, and then we put the stop signal. So let's start looking at our code here. We declare 2 bytes, that's where we're gonna receive the data. And it's really a good idea to initialize them to something. Just anything that kind of stands out. And basically, if you look at the bytes after the transmission and you see them, they remain at these 2 values, then you know the communication has failed. So this is how I would know whether the communication was successful or it didn't go through. One reason is important to initialize these 2 variables is if you, let's say we didn't initialize them and you did the communication once and this became 47, this became 42. So everything works fine. If you modify the code and it breaks, it doesn't work anymore. And if you run it one more time, this could remain 47 and 42 because the memory has not been flushed, right? Typically you have your microcontroller connected and you compile multiple codes and test them, right? So you may get 47, 42 because this is how it worked when you did 2 compilations ago. So this is why, to prevent against this, they will be initialized every time, and only if the things work correctly, this will become 47, 42. So that's a good idea to initialize. Remember, this is the rule of the, one of the rules says initialize all the variables always. So that kind of goes here. Let's initialize some other variables. So we have a variable called address, and we're gonna write there 33. This is the I2C address we will communicate with. We're gonna go to this register called control CTL, and we're gonna assert this bit called UCTR. And this bit, when you assert it to 1, it means the RW will be equal to W, because the first thing we're gonna do is we're gonna write the register address 70. And that's what you see here. We will go to transmit buffer and write 70. So you can see these three things together, saying we want to communicate with I2C 33, and we're gonna do a write, and that's what we're gonna write. Once all of these things are set up, then we're gonna do the start signal. So we go to the same register, assert the start signal, and that means immediately the start signal will be transmitted and all of these three guys will take effect. So you can notice that you're gonna set the things up first and then you will do the start signal. Because if you do the start signal first, these guys are not ready, then the module is not gonna do the correct I2C actions. So that's one thing we can learn when we program a communication protocol. You make the things ready and then you fire the bit. And once this fires, everything is ready. We'll go on the exchange step by step as they're supposed to go. Next thing we're gonna do is we're gonna wait for this signal to go back to 0. And instead of this line, there should be kind of like a while loop. This is kind of like pseudocode we're looking at here. So we can simply write a while loop while STT inside this register is 1. We can simply cycle in the while loop. So wait for this to become 0. When this bit becomes 0, this means the start and the address have been communicated correctly. So the start address and the W bit have already been put on the bus. So this guy becomes 0. Let's start getting ready for the next operation, which is a read operation. So now we're gonna go to CTL and set UCTR to 0 because this means read. And we're gonna set the start signal. So as soon as this guy is written and it has been acknowledged, the repeated start will go through. Address will remain 33, so we don't have to write the address again. So this is the second part of our exchange. Since we are reading, we're gonna wait for the receive flag to become 1. So again, we could write a while loop, wait here in the while loop as long as the flag is 0. So now the receive flag is 1. We're gonna read the receive buffer and write this in byte 1. And this is where I expect to receive the first byte, which is hexadecimal 47. Now, at this point, we're still gonna read the second byte. And it turns out, when we are reading the last byte, we should set the stop signal. Because this is when I'm reading the second byte. As soon as the second byte is read, I want the stop signal to go immediately on the exchange. So the rule that we have here is before reading the last byte, that's where you set the stop signal. So as soon as the last byte is read, the stop signal will go out immediately. Obviously, this is my last byte. I'm only reading 2 bytes. So before reading the last byte, we're gonna go to CTL and set the stop signal. So it goes as soon as the byte is received. All right. When you read the receive buffer, this clear the flag. So I'm gonna wait for the flag one more time to become true. There would be a while loop here. And when that occurs, we're gonna get the receive buffer and write this in byte 2. So now I would expect to receive the second byte, which is 42. Before we finish this code, let's pretend this code is a function. We're gonna write a while loop to wait for stop to become 0. I asserted the stop. When the stop signal is transmitted, this becomes a 0. And that means the whole I2C exchange is finished. So Last thing we're gonna do is merge the 2 bytes. So let's take the byte 1, shifted left by 8 bits, and let's take the byte 2 and OR it with hexadecimal FF. Sorry, instead of AND, this should be OR, right? We wanna OR these 2 guys together and put this in data. If data is passed by reference, then you would do start data equal. And obviously that's a 16-bit variable. So basically you wanna join the 2 bytes into one variable. So before we finish with this, before we finish looking at this piece of code, you can really see what's the important part or the key point in programming the I2C exchange is you gotta make the things ready before they're supposed to occur, because you don't want the exchange to wait for you. The I2C exchange should be going at kind of like full speed. It should not stop and wait for the variables to be filled up, right? That's why we filled up I2C address with W, and that's what we're gonna write. Only then we fire the start signal, and these guys took place, did what they're supposed to do. Same here. Now we change the bit to R, and only then we fire the start signal again. And you can see it here that you make the stop bit ready before you receive the last byte. So as soon as the last byte is received, the stop will go through. So that's kind of like the key point when it comes to programming these things. Next, we're gonna look at the light sensor. This light sensor is the one in the lab 9, and we communicate with this guy via I2C. So we're gonna see how this sensor gives back the results. So this is the sensor model number, is also made by TI, the optical 3001, and it has this 16-bit register. It has multiple internal registers, kind of like our example, and the result register is 16-bit. That's how we get the value, the light reading. This is the interpretation of the 16-bit result. It has a 4-bit exponent and a 12-bit value. And the way it works is we have a 12-bit value. So this counts from 0 up to 4095. So if you just look at this value, this goes from 0 up to 4095, which is 2 to the 12 minus 1. We're gonna take this value and we're gonna multiply it by a number which is designated by the exponent. So this is how it works. If the exponent is equal to 0, this means every bit or every 1 here is worth 0.01 lux. Lux is the unit to read the light. So the maximum value will be if you get the largest number, 4095, multiply by 0.01, you get 40.95 lux. So basically what you have to do is simply take this guy here and multiply it by the number that you see here, right? If this is the largest, 4095, you multiply by this, you get 40.95. That's the full range, means the largest lux value that you can measure. So let's skip a little bit, go to exponent 5. So if exponent is 5, the least significant bit's worth is 0.32 lux. So that means I will read this guy, multiply by 0.32. If you take the max value, 4095, multiply by here, you get 1310.40 lux. So let's skip a little bit, skip a few values to 9. Now LSB's worth is 5.12, which gives a full range of 20,966 lux. And finally, that's the largest exponent, 11. It makes LSB's worth of 20.48, which gives a full range of 83,000 lux. So let's look at the trade-off between the exponent. We got exponent 0 all the way up to exponent 11. So if you go toward the exponent 0, the full range will be quite small, but we actually gain resolution because now we're gonna get values in increment of 0.01 lux. So the value earlier than this would be 40.94, 40.93, 40.92. So this will be our incrementation step, which is a very good resolution. So if you want to have a great resolution, the problem we're going to be limited to measuring small lux values. On the other hand, if we want to measure really large values, we have to go up, increase the exponent. So let's say we're at this value here. We can measure up to 20,000 lux, but now our steps are 5.12, right? So if we're measuring 10, the next step would be 15, 20, 21. We're gonna jump up by 5 luxes. So we lose resolution. But the benefit is we can measure large lux values. You can see here, the resolution is 20 lux. So our increment is 20 lux. But it turns out in scientific cases, that's actually what makes sense. If you're measuring small values, usually you need accuracy. If you're measuring really large values, accuracy is not as important. So the experiment in lab 9, we're supposed to measure the lux values in a classroom, and that, I believe it's about 1,000 lux. So we would need to set it somewhere in the exponent between 5 and 9. We can go a bit more than 1,000. So you can test, like, if you flash your cell phone's LED on it, you can go up to maybe 8,000 lux, for example. Let's look at the exponent 12. If we set the exponent to 12, this means the sensor is gonna choose the most suitable exponent. So either one of the choices from here all the way up to here. So what the sensor is really gonna do, if we are measuring low lux values, the sensor is gonna bring the exponent up toward the small exponents, so we have more accuracy. And then all of a sudden, if we started to measure high lux values, the sensor is gonna bring the exponent higher, so we can accommodate these high values. So it will keep adapting, staying as high as possible to give the best resolution, but to also have a full range that can really measure what we're trying the values we're trying to measure. So last thing we're gonna talk about is the configuration register. So other than the result register, the sensor has a configuration register. And inside the configuration register, you can request any of the exponents you want. If you want the exponent 12, you can write here 12. And that means when you read the result, the exponent could be anything, right? Because when you select 12 in the configuration, the actual exponent can be anything. So here you're gonna get the number 0 to 11. So you figure out what to multiply the result with. Now, here is the catch. What if I want to use exponent 9? So if I went to the configuration and I set the exponent to 9, then when I read the result, the exponent will be 9 every time, right? Because I already set it to 9. So every time I read the result, the exponent will be 9. So this could be a bit annoying because we have to get rid of these 4 bits before I multiply with 5.12. That's why we have a feature called mask exponent. So if I choose the exponent to be 9, I can mask the exponent, so these 4 bits will come as zeros. So as soon as I read the result register, which is 16-bit, I take all of it. These will be zeros. I will take all of it and multiply by 5.12. So this makes the operation a bit simpler. You don't have to shift to get rid of the exponent. It will be zeroed out automatically. And we just multiply by 5.12. So last thing we're gonna discuss about this operation is what happens when we multiply by a floating point number. Because it turns out that MSP 430 has very few assembly instructions and it really doesn't support floating points. I don't even think it has multiplications. So it has no multiplications, it has no floating point operations. So can I really take this guy, multiply it by 5.12 and everything works? It turns out, yes, it will work because the compiler is gonna do the work for us. So the compiler is gonna generate work that's equivalent to multiplying by 5.12 and the value will be transmitted correctly. Of course, the value will be integer because our registers are integers, but that would make it work. So in Code Composer Studio, once we receive the result register, just multiply by 512 and we will have our LUX reading.